Okay, so we're now going to look at the combustion in air. So combustion in air can be in excess air, in theoretical air, or in deprived air, which is known as incomplete combustion. So in excess air, it is, let me start with theoretical air. Theoretical air is stoichiometric air, which is the exact amount of air which is needed for combustion, the exact amount of air which is needed for combustion of a fuel. So like we saw before in the last equation that we did, that was the theoretical air, which is 100%. Excess air is when we've got more air. When we've got 150% theoretical air, it means that we've got 50% excess air. So 150% theoretical air is equal to 50% excess air. Then if we have deprived air, then that's where we have less than 100% theoretical air. Okay, so with theoretical air, we've already looked at it. Theoretical air is from the examples that we were just doing right now. So now what we're going to do is we're going to look at excess air. So for combustion in excess air, like I said before, it is when you are given more oxygen or more air than needed. So we have to look at these terms: excess air and theoretical. So when we say excess air, we mean it's more than, so 50% excess air is 150% theoretical air. 100% excess air is 200% theoretical air. So what we're going to do now is we're going to do an example. So the example we're going to do is for methane. So let's say we've been given methane and it's going to react in 50% excess air. So methane in 50% excess, or 150% theoretical air. So what we do is first we start with the original equation. So the original equation, like we had before, is CH4 plus 2.76 to okay. So now for us to have excess air, what happens is first we start with the fuel, it remains the same. Where we change is with the air. So we said it's 150%, which means it's multiplied by a factor of 1.5. In this case, the carbon dioxide and the water remains the same if it's theoretical air. So CO2, sorry, if it's excess air, CO2 plus 2H2O will remain the same. Then we change the number of nitrogen molecules. So what we do is we multiply 1.5 times 2 times 3.76, or we can just do it straightforward and say 1.5 times 7.52, which is 1.5 times 7.52, okay, which is equal to 11.28. Then since we also have excess oxygen, we add an oxygen. So this oxygen that we have added, we see the oxygens that are this side. How many are this side? 4. Then how many are this side? 6. So because it's 1.5 times 2, 3, 2, which is 6 there. So in order for us to balance out 6 this side, we put a 2 here. So this is how we solve for excess air. Then let's try and find the air-fuel ratio. So we'll start with the air-fuel mole ratio. So the air-fuel mole ratio for air will be equal to 3 plus 11.28 over 1, which is equal to 14.28. Then the air-fuel ratio mass is equal to air-fuel mole times molecular mass of air over molecular mass of the fuel. This is molecular mass and not mass, okay? So which would be equal to 14.28 times 28.97 over 16.043, which is equal to 25.79. Okay, so with that in mind, now I'm going to introduce you to another term. So this term is called the equivalence ratio. This equivalence ratio is denoted by this symbol. So the equivalence ratio is the ratio of the air-fuel ratio of the standard air-fuel ratio over the actual air-fuel ratio. So the air-fuel standard ratio is the air-fuel ratio of the theoretical air. Then the air-fuel actual is the one of which you are from doing. Okay, so this goes for both the air-fuel. We have the equivalence for mole and the equivalence for the mass. Okay, so we're just going to solve examples using the equations that we already had. So we're going to start with the equivalence mole. Okay, so the mole equivalence, we're going to use the equations for methane. Okay, so for mole we have AF standard over AF actual. So the AF standard is the one we did at first, and then the AF actual is the one we're just from doing, which is the one which is here. So the AFS over AF will be equal to 9.52 over 14.28, which will give us 0.667. Okay, then we're also going to have the mass, equivalence ratio of the mass, which is equal to AFS over AF, which is equal to 17.24 over 25.79, which is equal to 17.24 divided by 25.79, 0.668, which is approximately the same. So what we're now going to do is try the inverse of this. So the inverse, so note that these the equivalence ratio, both mole and mass, are the same. They are equal to each other. So the inverse of the equivalence ratio is equal to, so 1 divided by answer, approximately 1.5. So this 1.5 tells us that our theoretical air was at 150% theoretical air. Okay, so after this, now we're going to do incomplete combustion. So incomplete combustion is basically when we have less oxygen, less oxygen or less air than theoretical reacting with the fuel, or needed to react with the fuel. So what happens is we will have the fuel plus the air, which will give us carbon dioxide plus water. Then we're also going to have carbon monoxide due to insufficient oxygen. So when you're given this kind of equation, what you're supposed to do is when you write the fuel, then the air, the first thing we do is we make sure that the number of hydrogens is equal to the number of hydrogens in the fuel this side, which gives the H2O this side. Okay, then after that we'll look at the remaining. We just write C, so we just put here, let's say N is the number, codifies it to make it the number of hydrogens this side. Then we just put a CO2 here and a CO here. So what happens now is the remainder of the oxygen and the carbon. So the carbon, the amount of carbon that will remain here, and the amount of oxygen. Okay, so let's say we have the N2 value already, because the N2 does not change. The N2 is just the same, it does not react with anything else. So we just say B, N2. So like I said before, first you make sure that this is sorted out. All the water that reacts comes this side, and then the N2 is also here. Then we remain with the CO and the CO2. Then the amount of carbon and the amount of oxygen that remains, we balance it out with the carbon dioxide and carbon monoxide. So first we sort out the water and the nitrogen, then the remainders are balanced. We balance out the equation with the CO2 and the CO.